Hi, I'm Olof Danielsson. I work for Volvo Construction Equipment. My presentation is about digital twins in the construction machine industry. At Volvo, I had a department called Virtual Product Development, and I'm based in Sweden. I'm also pursuing a PhD at a local university in Sweden. I will explain topics about digital twins in general terms, as well as specifically for Volvo Construction Equipment. So the topics include background, digital twin definition, and use cases that we have at Volvo, and some lessons learned. Let's start by looking at the company and our industrial presence globally. We are part of the Volvo Group, and we operate across all continents. We develop, sell, and maintain construction machines such as excavators, haulers, wheel loaders, compactors, and pavers. So a bit on the background. Traditionally, practices in product development, sales, and aftermarket were heavily reliant on experienced people. Now we're seeing a shift due to rise of data-driven efficiency, sustainability imperative, reimagining maintenance, and more transfer to subscription-based business models. So the digital twin journey at Volvo, it started a long time ago. I'd say in the 80s with we did finite element analysis, and we did load measurements on physical machines. Over the years, we integrated virtual simulations and finite element analysis. We developed methods for complete machine simulations, and we transferred to new modern ways of doing stress analysis. In 2012, we started with defining smart data logs on the machines, and they were implemented on every machine. It took a few years, but it's done since 2020. We started collaborations with universities, and we engaged with industrial PhDs, and worked a lot with data science and machine learning. And this is development. It's not finished. It will continue for many years still to come. So we are continuously improving this. We define the digital twin as a virtual counterpart mirroring the real world behavior. And they're used, I should say, the real world behavior, also the characteristics and the environment where the machines are used. And it follows the evolution of the system in time. So it's used across its lifetime. Other areas where digital twins are used is in smart cities, agriculture, healthcare, and automotive and construction. And the purpose is to create insights. It's also to streamline processes and enhance service deliveries and facilitate decision-making in many parts of the company. The core elements of digital twins is that we have a physical reality. We have a virtual representation of this physical reality, including both the machine and the environment in which it is operated at the customers. And then we have a connection between the physical and the virtual worlds, where we exchange data in both directions. There's one important thing is about the frequency of the model update, and this should be tailored to specific use cases depending on what you're using it for. Many say that it must be updated in real time, but for some use cases that's not necessary. So we define, for most use cases we have at Volvo, we are not updating it in real time, but it's enough to know the data maybe update once a week or so. So the difference between traditional digital models and digital twins is that the digital twin represents one single instance of the corresponding physical twin and not a class or fleet of machines. And then we have the digital twin updates its model as it changes over time. And so you can see here we have in the virtual world, we make simulations on how machines behave, and also how this is stress analysis components. And we, together with sensor data on the machines, we connect that with mathematical algorithms. And on that, we do data analytics. This is very advanced mathematics here. And one end product from this is a figure like this, where it shows, we call it remaining useful life. We have machine hours on the x-axis, and then we have the degradation of the component's condition here. So we can see after a certain amount of hours, we have how much left of the life of this component. Based on that, we can plan for maintenance. The digital twin, for us, we started in product development and then moved over to maintenance, but we can see that we can use it in all phases of the machine, from specification to disposal. And there are different use cases in every phase. If I come furthest in this part, but we have started in all the phases. Some applications for us of the digital twins. I have two examples. One is component remaining useful life rule for predictive maintenance and predictive logistics. This is very important because we have machines in very remote locations, and if a component breaks, it is really bad if we don't know it in advance. It takes a long time to get parts to that. The other thing that is quite big for us is that we can predict component life in new machine design. So these are two use cases I will shortly describe. For the component remaining useful life for predictive maintenance and logistics, we can see these are rule curves, and we can see on a map where this machine is. I mean, this can be all over the world. So this is a typical dashboard that we create for our customers. So in new product development, digital twins, they predict component life as if it was already in operation, providing virtual testing and customer users insights. This is kind of a hybrid solution involving both new machine that is in early phases only exists in the virtual world. We don't have a physical prototype. And we use customer data from physical machines. So this is the new generation machines we design right now. We use this hybrid technology. Some lessons learned since, as I told you, it's been from early 80s. That was before my time, but we build up on that. So we learned a lot about algorithm development and the importance of collaboration, because to get these algorithms onto the machines and in the cloud, so many different departments are involved. So we learned a lot about that, and we need also this early customer involvement. Sometimes very good ideas, we think, come up in product development, but if that's not discussed with those who are very close to customers, sometimes the ideas is not so great for the customer, and then it's a waste. So we need to involve customers very early when we do the algorithms. Alignment with test departments. Several test departments is involved. So they need to be involved very early in the planning phase. Improvement of sub-processes. In the end, if the outcome from the digital twin is not as expected, it can depend on that different parts in the digital twin is not accurate enough. So we have been, when we tried it, we saw that the result was not what we expected. We have to dig deep into different parts of the digital twin. And so we have, for example, we had to improve the accuracy in the fatigue life assessments. So that was a quite big thing. And some of the things are still ongoing. So that was everything. Thanks for your attention.